Hey, howdy everybody. Last time we got into facies modeling, talked about the MPS, multiple point simulation, and object-based simulation, and we talked about the general modeling workflow. And the general modeling workflow will typically, for the subsurface, will involve a series of steps going from facies, and then within facies, continuous properties, and in the case of oil and gas, it would be porosity, and then permeability, constrained by porosity to have the right correlation between the two. So this lecture right here will fill in that piece. How do we take a continuous model within a facies framework and simulate multiple variables? How do we get beyond just a single variable? How do we go to what we term as cosimulation? So what's the motivation for cosimulation? Well, typically we have to build a reservoir model of more than one property. We don't want to build reservoir models of just porosity or subsurface models of just porosity. We need to know about the permeability, saturations of different fluids. Maybe we're even working with models where we need elastic properties for geophysics, or we need geomechanical properties, the stiffness of the material, its behaviors mechanically, and so forth. So the typical workflow that we talked about before for oil and gas, which is quite common, would be build a facies model, have your realizations of facies. Within the facies realizations, simulate the porosity. And then within the realizations, co-simulate the permeability as a primary variable, correlate it to the previously simulated porosity realization. Everything is paired up. You have a realization of facies. In each of the facies, you have a realization of porosity and permeability, and the porosity permeability realizations are paired to each other. They're correlated to each other. They're constrained. We will only talk about the most commonly applied cosimulation methods. We'll talk about collocated cokriging and the cloud transform. Collocated cokriging will just be an extension of our kriging system. Cloud transform is quite a bit different, but it is quite intuitive. And we'll only limit ourselves to workflows that are bivariate, 2 variables at a time. We're not going to be talking about some of these more advanced type of workflows that are able to account for massive multivariate type of subsurface modeling. Very interesting topic, but we wouldn't have time to cover that right now. Cosimulation is not perfect, but the alternative to cosimulation would be to simulate each property independently. So imagine we did that. Imagine we had porosity and water saturation, and the data looked like this, and the R value, the correlation coefficient, linear correlation coefficient, was 0.76. Pretty good correlation coefficient, you can see, and that should in fact be a negative 0.76, right? It looks like a negative relationship. Now, if we were to simulate them separately, we simulate a realization of porosity at all locations in the reservoir model, and we simulate a realization of water saturation at all locations within a model with no cosimulation, no constraint between the two. You could expect to see a relationship like this. In fact, if you saw any correlation at all, it would be simply because the correlation at the data locations was being propagated into the model. But outside the range of correlation of the data, there would be absolutely no correlation. They'd be just independent of each other. Yeah, that's pretty bad. That would be, we'd have lots of implausible combinations. You see that typically if we had a high porosity, we tended to have a low water saturation. Well, we'd be simulating values with combinations of low porosity, high water saturation, which wouldn't be physically plausible given this setting. And in fact, if you think about it, that'd be introducing a lot of uncertainty in the model. And so it wouldn't be physically plausible, and it would add a lot of uncertainty. So we want to do cosimulation. Now, cosimulation is pretty good. If you take the data, you look at its plot again, its relationship, and you go ahead and you cosimulate, you might get something like this. And this cosimulation, we'd have to look at the summary statistics and so forth. The main message we'd like to communicate here is the fact that it's not perfect. We may not honor the complete perfect bivariate relationship, and if we do, we may not honor the varogram and the histogram perfectly. There's going to be some compromises, and we'll talk about those, but we will capture the general trends, the general relationships, and so it's much improved. Now I want to kind of reinforce this idea of pairing the simulated realizations. That is, if we're co-simulating permeability as the primary variable, where it will be related to the secondary variable, porosity, then we will be pairing up the realizations. Realization number 1 of porosity will be used to constrain realization number 1 of permeability. And in fact, it goes further. If we were to look at the simulated value at location U1, a location within this model, it will be paired up with the previously simulated value of porosity, and that will be used to constrain what happens in the simulation of permeability based on the strength of the correlation. And you will enforce the bivariate relationship, correlation coefficient, the shape of the scatter plot between porosity and permeability, to be enforced at each one of those locations. And so you could even calculate that previous plot that I showed was in fact taking this location as a pair and plotting it on the scatter plot right here. Porosity, saturation. Well, for this case, of course, it's porosity and permeability, but all the same. Then we would scan over all possible locations, get all possible pairs of one variable versus the other one, the ones that are all of the values that are coincidental with each other spatially, they're in the same location. And we plot them, and that's exactly how we plot it and how we would check the relationship between the two variables. All right. So let's go ahead and talk about each of the methods that we will talk about. Collocated cokriging is a methodology that focuses on using the kriging system to reproduce the histogram and the varogram, and may honor the correlation coefficient, the linear correlation coefficient between the two variables. Does a pretty good job with that. But the cloud transform is a method that will honor the specific form of the bivariate relationship. If it's a little bit curvilinear, if there's heterogeneity, if there's complicated constraints, cloud transform is your methodology if you need to reproduce that. But it may not honor the histogram nor the varogram precisely. So it's a case of each method has its own weaknesses. Collocated cokriging, if you want to make sure you get the histogram and varogram right, and you're comfortable just getting the correlation coefficient okay between the two variables, would be this method right here. You got the general direction of correlation. It's not perfectly reproduced. You don't reproduce exactly the same form of the bivariate relationship. That's collocated cokriging. Cloud transform, you'd be able to reproduce the exact form of the bivariate relationship, exact shape, and so forth, but you may not honor the histogram nor the varogram. Both of these methods will start with a complete realization of the secondary variable. So in the workflow, you first simulate a realization of the secondary variable, porosity if we're co-simulating permeability, or saturation as in the previous example. And so you start with that realization. Use regular simulation to get the first realization of the secondary variable, and then use co-simulation to get a realization of the primary variable, in this case being saturation or permeability, constrained by that porosity. So in order to talk about co-simulation, we got to know something about cross varograms. And so you'll note we go very light here. This is very cursory descriptions here. We won't dive into too many details. A cross varogram is a measure of how two variables differ together over a distance. If you look at this equation, you'll readily see that all we did was we took the varogram equation, which was the tail minus the head squared, and we expanded it out, and we replaced the second term with another variable y. So now we've got a cross varogram between z and y. And so this is a measure of how two variables will vary together over a distance. Now it makes sense that we can do the same thing for the covariance to get a cross covariance. And so if we take the covariance equation, we expand it out, and we do the same thing to it. What's interesting here is we just changed the term in the head to be the other variable. And so here we're pairing points that are centered by their means, the value at location u, the tail location, minus its mean, times the value at location y at the head location, minus its mean. So we're taking two values in space and we're comparing them offset by lag vector h, but we're comparing one variable at the tail to another variable at the head location. And so of course we can expand that out, and if you have zero mean, of course this will just simplify for us and just become the product of the z variable at the tail times the y variable at the head, and that would be the cross covariance for lag vector h between variables z and y. Now of course we can take that, and if we standardize by the by the standard deviation of z times the standard deviation of y, we get a cross correlogram. And this is pretty cool because this in fact becomes a plot of the correlation coefficient between the two variables versus lag distance. So that's a pretty powerful concept of correlation over space. What does it look like? Well, if you plot them up, this is what you would get. The cross variogram, just like a regular old variogram, going to start at 0, and as the lag distance increases, it will increase and will level out at its sill, and the sill, as h reaches the range and goes further, is equal to the correlation coefficient between the two variables. We say correlogram at 0 distance, that's the correlation coefficient between the two variables. Easy. Now, what's very interesting though, is you could have a negative correlation. And if you have a negative correlation, your cross variogram will go negative. From 0, it will go negative. It'll drop until it reaches the negative correlation coefficient, and then it'll level out. That's the cross variogram. The cross correlogram, now that's pretty interesting. And once again, of course, if we're talking about cross correlogram, if the standard deviation of y and x is standardized to be equal to 1, then you will basically have a cross covariance that's equal to a cross correlogram. And so we'll just talk about cross correlograms now. And so what will it do is the cross, I just found a mistake and fixed it. So the cross correlogram will start at the correlation coefficient. So right here, if it was a positive correlation coefficient, or it could start right here if it was a negative correlation coefficient. And at the distance of the range, it will rise if negative, it will drop if positive, and it will reach 0. And at the range, there is no correlation between the two variables. And so this is a very powerful concept. And so we can see the behaviors. Once again, we also have the relationship that the variogram, the cross variogram, is equal to the correlation coefficient minus the cross correlogram. So the same type of mirror image type of relationship between the two that we saw between the variogram, the sill, and the covariance before. Now, here's something really cool about kriging. The kriging methodology is completely general. We could, in fact, as we saw before, we can build a kriging matrix with all of the covariances between all of the data in themselves, the weights here in the weight matrix, and all the correlations, the covariances between all of the data and the unknown locations. This part of the system, the yellow, and the weights right here, we already know that's a simple kriging system. Now it turns out that the kriging system is completely general. In fact, if you had a whole bunch of different secondary information at different locations and you want to also calculate their weights, another variable, you could just include them. And if you include them, this whole thing would expand out and you'd have a matrix right here, which would be the covariances between all of the secondary and primary data, the covariances between all the secondary and primary data, and the covariances between all of the secondary data themselves. And this component of the right-hand side would be the covariances between all of the secondary data and the unknown location, which is a primary data. And so this would be a direct covariances, which would be your typical covariances of the primary, typical covariances of the secondary, but these would be cross covariances right here. And you would have a set of cross covariances between the data and the unknown locations. Now, it turns out that we can greatly simplify this system because up until now we would need to know the cross-variogram between the primary and secondary. We need to know the variogram of the secondary. And that would get kind of complicated. We'd have to form a positive definite model, including the primary and secondary data and the cross terms between the two, which is known as a linear model of co-regionalization, which we will not cover in this course. And it's a bit complicated to do. It's more kind of graduate level type of thing we would do. And so we don't want to deal with that. So the way we get around that is we say, let's do collocated cokriging. And what it'll do is we'll make two assumptions to simplify full cokriging, and we simplify it down to this matrix right here. Only one collocated secondary variable is considered. So by doing that, we get rid of the full matrix of possible secondary crosses and directs, and we say just take the one collocated secondary value and go ahead and include that within the system. And then we assume that the cross variogram, because we still need to know the cross covariance between the data, the secondary data and all the other primary data. And we just say that we can get that as a linear scaling of the regular direct variogram of the primary. So is this a reasonable assumption to make? Well, it turns out the collocated secondary value, if you have a secondary information, the secondary value data or realization at the same location that you're trying to estimate the primary variable, it's got zero distance offset. It's the most important value. It will screen the influence of all the other possible secondary data in the search neighborhood. So that's pretty reasonable. So let's go ahead and look at this assumption or this methodology more closely step by step. Let's build the collocated system. So first of all, let's talk about this idea of screening of the collocated value. And so what are we doing? We have a system like this. We're trying to make an estimate of the primary variable at U0, at location U0, given primary data at location 1 and 2, secondary data at location 3 and 4. This could be completely general. We could have secondary data at location 2 and 1. We could have any type of combination of secondary and primary data in space in order to make this estimate. So we get rid of the non-collocated secondary data. So we throw out location U4, U3. We only retain the value at this location right here, which in fact is U0. Excuse that. So we just retain that one secondary value, and we say that one's going to screen all of the other secondary data, and that we will call the Markov screening assumption. By doing that, we now get rid of the need to know the variogram of the secondary data. We only have one single secondary data, and in the matrix it's just going to be this value right here. It's going to be the correlation, covariance I should say, between the secondary data and itself, and that's just equal to the CIL. And if you standardize the CIL to be equal to 1, it's just 1. So that's super easy to do. Okay, so that's the first part of Markov, the Markov screening part of the collocated cokriging approach. The second approach is that, well, we still need to solve for these cross covariances between the secondary, retained secondary data right here, which let me go ahead and just put that in blue so that we remember it's different. I didn't quite get the right blue. Okay, between the secondary data and all of the other primary data here, we still need to know that. And so what do we have to do? We need a cross-variogram to do that. This is where we bring in a Bayesian updating assumption. You remember Bayesian updating from our days of probability, those days at the beginning of the term or the course. We talked about probability and frequentist and Bayesian perspectives. What we say is that the cross-variogram between the primary and the secondary, Z and Y, at lag distance h is equal to the correlation coefficient between primary and secondary, Z and Y, multiplied by the primary variogram, the variogram for Z at location H. We're rescaling the variogram by the correlation coefficient in order to update it to give us a cross variogram. And if you think about it, it's very logical, because if we have negative correlation. That will flip the variogram, so now it will drop till it reaches the sill. If it's positive, the variogram will now rise up to the sill of the correlation coefficient. And once again, remember that we're working with in Gaussian framework here, so the sill is going to be equal to 1. So all of this is going to work for us. Take the sill, multiply by the correlation coefficient. The new sill is the correlation coefficient, as we see with the cross variograms. So it's actually, you assume the shape and the correlation is going to be the same. The range is the same. In the cross term, as the direct term, you're just rescaling it to account for the correlation coefficient. So what's very cool about this is we could populate this entire cokriging system of equations simply by knowing only one additional piece of information. All we needed to know is the correlation coefficient between the primary and secondary variables. And then we can go ahead and we can do a simulation or a kriging where we go through at all locations. We already have an exhaustive secondary data set, the simulated realization of, say, porosity, if we're now working with permeability, that's available to us. We can, for every possible location, we have the collocated secondary variable, and we can now do our kriging, including it and using the correlation coefficient in order to get these cross terms. So, once again, the power of this approach is by retaining only the collocated secondary variable, secondary data. There's no need for a variogram of the secondary variable. We don't need that. We don't need the variogram between secondary data and secondary data. No need for the cross variogram. We're going to just update it using the correlation coefficient. If the secondary data are smooth, then considering more collocated variables should not even help anyway. So this method should work pretty well. But there is a serious potential problem with excess variance in the results when used in the simulation mode. The excess variance is caused by the fact that we are throwing out information. We're not using all of the secondary data, and so it can cause a bit of a bias in the variance. And if this is detected, often what algorithms will do is they will just scale the variance back so that the total variance is correct. And so that's a general approach. Just once again to emphasize this idea of updating the variogram, if this was the original variogram of the primary variable, shown here with 3 different structures, you can see the inflection points. This is the sill equal to the variance of the primary variable. This is the sill equal to the correlation coefficient between the 2 variables. Rescaling red, the primary variogram, simply gives us this variogram right here. Same shape, same range, different sill. That's all. That's all we have to do. So let's go ahead and look at a typical workflow right now. So we have our secondary information, and that could be a simulated field of some property. Maybe it's based on seismic information, like here it's an acoustic impedance. Maybe the acoustic impedance is just available to us at all locations and we don't need to simulate it. That's perfectly okay. One way or the other, we have a secondary variable that's available to us at all locations for which we want to simulate the primary variable, which in this case is porosity. We're going to transform each of the variables to Gaussian. Normal score transform of seismic acoustic impedance, normal score transform of porosity. We're going to calculate the correlation coefficient after normal score. Why do we do normal score first? The simulation proceeds within Gaussian space. Everything is Gaussian. The correlation coefficient should be of the Gaussian transform, just as much as the variogram should be of the Gaussian transform as we saw before. Then what we're going to do is we're going to then, at every single location that we simulate porosity, we're going to take that collocated secondary information from this other realization or model. We're going to include it into the kriging system. We're going to be able to calculate the cross variogram terms to populate the kriging matrix based on the correlation coefficient of 0.41, scaling the variogram of porosity so that it has the right sill as a cross variogram. And we can go ahead and we can proceed. You imagine you got a random path all throughout this model to simulate the porosity within the facies. Every location, you go and you check what the acoustic impedance value is. You include it in the kriging system. You use all of the scaled direct variogram terms in the covariance matrix to get the cross terms, and away you go. That is collocated cokriging. That's all I think I have about it, and here's a nice example of it being used in order to do a simulation to capture the correlation between two variables between the realizations. And so this is one way to be able to get into a model the concept of correlation between variables such as porosity and permeability, saturation and porosity, and so forth. Now another method we want to talk about was this PField and cloud transform type of methods. The reason we bring them up is actually PField is, or specifically cloud transform, is used all the time. Pyrcz, GoCAD, other types of software programs, they have collocated cokriging, but you'll find cloud transform is used an awful lot. So the key idea of PField is to perform a simulation in two steps: construct the local distributions of uncertainty, and then draw from those distributions simultaneously with correlated probability values. So we're separating the simulation approach into two distinct steps. Now you recall with the sequential methodology, at every location we calculate the local distribution of uncertainty. We do Monte Carlo simulation, and the correlation is imposed in the kriging. In this methodology, the correlation is not imposed in the formulation of the local distribution of uncertainty, but as a separate step. The advantage is distributions of uncertainty can be constructed to honor all kinds of data. You can check them before you make the realizations. You can pre-calculate them. You could incorporate other types of information to update them, and you could observe directly how they're being updated. So it can be very powerful. If you imagine I'm trying to do Bayesian updating, as we've talked about before, I've got some type of, I treat that as a prior. I've got some type of likelihood, and I could update them with additional information. That could be done. Simulations are consistent with the distributions of uncertainty then. Okay, so also there's good reproduction of primary to secondary data in the scatter plot. This methodology is very good at getting whatever the form of the bivariate relationship is, you can get it back. You'll get back pretty close to that form. Some disadvantages include potentially poor reproduction of the histogram and the variogram. You'll see this methodology in doing all of this may actually change the variogram. The variogram may not be completely correct and so forth, and I'll show you that. And it's the most common approach within this PField family of approaches is known as cloud transform, which is commonly used in workflows in industry for simulating permeability conditional to porosity. What does PField look like? Let's just take a very simple example. We got the data values. This is a one-dimensional example. We got an x-coordinate right here. I should give credit. This figure is actually from the book with Clayton Deutsch. Appreciation. I'm using my lecture materials here. So data values are located here. We're now trying to simulate our all locations in 1D, 1 through 10. We would formulate the local distributions of uncertainty. In fact, you could do this by kriging. You could krig and calculate at every single location what is the, now not sequential kriging, but just regular kriging. We get the estimate and we get the uncertainty at every location. That would be perfectly fine. Then what you do is you have these distributions of uncertainty. You want to draw from them in order to build a simulated model. You can't draw randomly from each one of them, or you would not reproduce the spatial continuity. You can't draw the mean value at each location, or that would just be kriging, and we know that that's too smooth. So Mohan Srivastava and others, when they came up with this idea of PField simulation, they said, why don't we just build p-values, the probability values that we're going to draw from these distributions with spatial correlation. So you put spatial correlation in the p-values. So look at the p-values are uniformly distributed between 0 and 1, but they have spatial correlation. This realization number 1 is the blue triangles. And you notice that they're spatially correlated. Red squares, spatially correlated. Green diamonds, spatially correlated with each other. 3 different realizations. Then what you do with those p-values is you simply just draw from the distributions of uncertainty. Is it conditional? Well, at the data locations, the distribution of uncertainty shrinks to the data values. So with PField simulation, we can actually build models that honor the data, that have the right spatial continuity as imposed through this correlated probability values that are used to draw from the distributions. So it's a nice little methodology. The cloud transform method is a little bit different. What they do with this method is, in fact, we take the bivariate distribution, porosity and permeability, we bin it. Now what's very cool is we look at the location at which we want to simulate, and we look at the secondary information, porosity, and we now look at which bin is it in. And it's in this bin right here. It's a porosity value between 10 and 12.5%. So we build the conditional distribution of values that could be right here, and then we draw from that with Monte Carlo simulation, and we get a permeability value, or whatever the primary variable is, conditional or constrained by this relationship between the two variables. If you do that, Cloud Transform will in fact honor the precise form of this distribution as binned into these conditional distributions. Why is this attractive for the purpose of permeability? It turns out that when it comes to permeability, we often don't have a lot of data. The histogram is kind of poorly known. The varogram is difficult to calculate. And so this is not too bad of a methodology from the standpoint that the cross plot between porosity and permeability is probably the most certain information we have. And we're okay with a bit of imprecision with reproduction of the histogram and the varogram. Once again, of course, with this methodology, you could impart correlation within the p-values that are used to draw from these distributions, and a little bit of a numerical detail here. We condition to local data within permeability by constraining the PField to be conditioned to the specific probability value within this conditional that would result in the actual data value that's at that location. So what have we covered? What have we seen here? Well, cosimulation includes methods that are able to simulate a property realization, a primary, conditional to previously simulated property realization, which we will call the secondary. Two simulated properties without cosimulation will only have correlations imposed by data, and outside the range of correlation between the data, the spatial correlation range, they'll become uncorrelated. So you will not reproduce the right correlation between the two variables. So you can't go ahead and just simulate porosity, permeability, saturation independently. You have to constrain them with each other. You have to use cosimulation, the primary and secondary data type of approach. If you don't, it leads to unrealistic values. You could have combinations of porosity and permeability that don't even exist, and you have too high spatial uncertainty. That porosity information is useful for constraining the permeability information. Two methods have been discussed in this lecture. Collocated cokriging. We take the full cokriging system. We never showed you that, but we talked about what it would look like. You'd expand it out. And we apply a Markov assumption. We only need the collocated secondary data. Anything past that will be masked, Markov screening, and it won't be as important. We'll just ignore it. And by doing that, we didn't need the varogram of the secondary variable. We don't have to worry about that. Bayesian updating, we still need the cross varogram between the secondary and the primary because we have that one retained secondary within the system, and we get it by scaling the primary varogram with the correlation coefficient. Now note, this may not reproduce the cloud or the bivariate relationship very well, the relationship between the two variables. It's only constrained by the correlation coefficient, the linear correlation coefficient between the two. So if there's complicated nonlinear model relationships between the primary and secondary, it's got heteroscedasticity or something like that, you're not going to get that back. We talked about the cloud transform. It forces the reproduction of the cloud. It uses the secondary information to find out which bin you're in the cloud, and then it draws from that conditional distribution in order to simulate. It uses a correlated probability field in order to get the right spatial continuity for the primary variable given the secondary, and it can condition the p-values to the data values within the conditional distribution so you honor the data. but it may make mistakes with spatial continuity, and the distributions, they may not be precisely honored. So you got to know your assumptions, got to know your steps when you make a choice about which type of simulation method to use. All right, cosimulation. I hope that that was helpful to you. I am happy to discuss any time. I'm Michael Pyrcz. I am a professor here at University of Texas at Austin. I'm also the Geostat guy on Twitter. I'm super easy to get a hold of. You can find my email on the website for my department, Twitter. You can go ahead and send me a message or DM me if you're interested, if you have any questions. All right, take care, y'all.